Hi, y'all. This is a new series on tech interview skills. I'm an ex-Google software engineer, and I conducted hundreds of interviews while I was there. Now I'm a professional tutor and interview coach, and my goal is to teach you the skills you need to fly through the interview process at the top tech companies. I work mainly with professional programmers who want to get a job at a higher paying company or transfer to a better role. So I'm assuming you have real world coding skills, and I'm here to improve your data structures and algorithms knowledge and build the skills for problem solving and coding quickly that you need for interviews. This will not only help you become a master interviewee, but also make you a better programmer in general. So today we're focusing on this LeetCode problem 105. If you haven't seen LeetCode, absolutely check that out. It has tons of practice interview problems, and you can only get better with practice. So I'm going to guide you through my 4-step technique to find and implement a solution to this puzzle. I really recommend an active engagement with this video, so try and stay one step ahead of me if you can. It's really tempting to just like look up the solution or like not engage your mind and just go, oh, that's the solution to this problem. But you don't really build any skills that way. You really have to be engaged and like struggle with the problem. And that's what makes you better at problem solving. I also want to say, as you're practicing, don't worry about time. It's much more important to build the habits of thinking clearly and developing your resources. Speed will come naturally with practice. So just be patient with yourself, both when you're practicing and in the interview. Time stress really only slows us down. So let's get started on this problem 105. So step one is to understand the problem. And I really have to emphasize this. Do not start coding until you understand the problem and you have a really clear idea of what approach you're going to take. A lot of people just jump in and start coding. They're like, okay, I know the result should be a tree, but you'll just tangle up your mind in knots. You have to really understand what you're doing before you get started. Coding, honestly, should be the easy part. So step one, we're going to understand this problem as deeply as we can. Okay, so this problem is to reconstruct a binary tree from a pre-order and an in-order traversal. In case you don't know, a pre-order traversal first visits visits a node, and then it visits the entire left subtree, and then visits the entire right subtree. So it goes 3, 9, we're done with the left subtree, and now we go 20 and 15 and then 7. 3, 9, 20, 15, 7 here. So that makes sense. At this point, we're verifying all of our knowledge and making sure that our assumptions are correct. And this is also incredibly important to be very careful when understanding the problem. An in-order traversal first visits the left subtree, then the root, and then the right subtree. So the in-order traversal goes 9, and then we visit the root, and then we visit this. So 15, and then 20, and then 7. So both of these traversals are recursive, and it's just about whether we visit we visit the root of any of the tree or any subtree before we visit its children or in between its children. So 9, 3, 15, 20, 7 is in order. So our assumptions are correct. The first thing that comes to mind, we're still just understanding the problem here and getting our bearings, is like, what if there's more than one possible solution? Like, what if you can't reconstruct, right? So, for example, I can think of 2 trees. 1, 1, and null. Or this one, 1, 1. So both of these, the pre-order traversal goes 1, 1, or sorry, pre-order traversal goes 1, 1, and the in order of this one goes 1, 1. whereas the pre-order of this goes 1, 1, and the in-order goes 1, 1. So we don't have any information, and the inputs for these two trees that we're supposed to output uh, is exactly the same. And so we have no way to know which one we're supposed to output. And so this shows that we don't have a complete understanding of the problem yet. So we're going to really dive in and find a complete understanding of the problem. So is there anything else that they say? Okay, the length is reasonable, the same length. They're sort of small. Pre-order and in-order consist of unique values. Okay, so that's really helpful. The nodes are uniquely labeled. Okay, great. So what else do we need to understand this problem? I think I'm clear on what I'm supposed to do. Of course, there are inputs where pre-order and in-order don't correspond to any tree, but I think that's guaranteed. So we can assume that they are, in fact, a pre-order and in-order traversal of some tree. So we don't need to worry about detecting if it's wrong. Okay, so I think that I have enough understanding of this problem, at least what's expected of me now. And so now we're going to move to step 2. Step 1 was understand the problem deeply, and now step 2 is generate ideas. Like what do we know that might help us here? Do not code yet. Again, don't code until we have a really clear path. So we're going to generate possible solutions. And a way that I like to do that is by trying to pretend I don't know this answer and try to solve the problem by hand and just see how I do it and trace my mental process. So we know the pre-order traversal and in-order traversal. Let's try and find out what this tree is. So why don't you take a moment here and pause the video and try for yourself. Try to see what method you would use just to reconstruct this one tree from these two traversals. And notice what you notice about how you did it. So go ahead and try that. So the first thing I know is that the root is 3 because the pre-order traversal always starts with the root. So we know the root is 3. But the rest is unclear. Like this could be in the right subtree. We don't know that it's in the left subtree. And so what information can we find that lets us know that 9 is in the left subtree? Well, here's to the left of the root. The root is in the middle here, and so we know everything on the left of the root in order traversal is on the left subtree. And so immediately I have an idea. What if we find the root and then we split the in-order traversal into 2 halves? So we know that this is the left subtree and this is the right subtree. And that matches our example. We have 9 on the left and 15, 20, and 7 on the right. Yeah, and I think we can carry this through recursively. So now that the problem is split up, we found a way, probably, to split the problem into 2 smaller subproblems, and that is all you need for recursive problems. Just break down the problem into a similar subproblem, and then use recursion to carry that idea to a complete solution. So all we need to do once we've split this is, so let's write something down. So we have 3 is the root, and so then 9 is the in-order traversal of the left subtree, and 15, 27 is the in-order traversal of the right subtree. So now we've split the problem partially into subproblems. We've split the big in-order traversal into 2 smaller in-order traversals. And now we need to somehow reconstruct the pre-order traversals that will go with it. And then we'll have a subproblem that looks exactly like the original problem, and we can use recursion. So how are we going to do that? take a moment and see if you can come up with an idea to find the pre-order traversals of the left and right subtrees. Pause the video if you need to. Take your time. What I noticed was that we can use the length. We know that there's exactly one thing on the left and three things on the right. So because of the way pre-order works, we know that the next one element's going to be for the left subtree. So 9 is the pre-order traversal of the left subtree. And then the next three elements after that are the pre-order traversal of the right subtree. So 20, 15, 7 are the pre-order traversal of the right subtree. So now we have two subproblems we have from this original problem. If we can construct 9 and 9, this is pre-order and in-order, and we can construct 20, 15, 7, and 15, 27, then we have the left subtree and the right subtree, and all we need to do is put the root 3 back on top, and we'll have our solution. So I have enough experience with recursion to know that the problem is essentially solved now, because we'll just do the same thing here. We will break this up into two subproblems, and then each of those will be broken up into two subproblems, and the solution will be clear. But in case you're not familiar with recursion, we can try doing that by hand. Let's see what happens. With recursive problems, it's really interesting. It's a really good idea to find the simplest possible base case. So what if we use this strategy on this extremely simple case and see if it reduces even further? So 9 is the root. 9 is the root. This is the left subproblem. 9 is the root. Yeah, and so then we're supposed to, the next step is to split this to the left and right of 9. So we get empty. Empty is the left subtree, is the in order of left subtree, and also empty is the in order of right subtree. So we have empties. And if we see this in our algorithm, we can just return an empty tree, and then we'll put it together and we'll get this 9 by itself. And so our base case can be if we're trying to reconstruct from an empty traversal. Like, we don't need to cover this case of a traversal with only one element, because it reduces using the same technique to a traversal with 0 elements. So 0 can be our base case. And then the right subproblem, just to show how it works and convince ourselves that the same approach will work. 20 is the root, because it's the first element of the pre-order traversal, and then we split the in-order traversal on this middle element. So 15 is the left in-order, and 7 is the right in-order. And then these both have length 1, so what were we going to do to find the pre-orders is just use the length. The next one element is the pre-order, is the left pre-order, and then the next one element after that is the right pre-order. Is the right pre-order. So we've reduced the problem to 15, 15, and 7, 7, and we've already seen a problem like that. So we can be very certain that this approach will continue to work. So at this point, I'm quite happy with, I'm pretty confident that this approach is going to work. Let's write down our approach just so it's easier to talk about and think about. So step 1, find root. Step 2, split the in-order traversal at the root to find left and right in-orders. and then use lengths of in orders to find left and right pre-orders. And now that we have a smaller similar subproblem, recurse. So that's the solution sketch. So now we start coding, right? Wrong. Now we move on to step 3, which is analyze the solution. Let's estimate. It doesn't have to be super accurate, but we want to estimate both the how difficult this is going to be to program and how expensive it is. If we have a solution that's extremely hard to program, we're not going to be able to do it in an hour, and we need to look for one that's going to be easier, or show that we've at least made some headway on the problem. And if it's more expensive than necessary, which is sometimes hard to tell, but by doing estimates, you can get a sense of maybe whether it can be improved. So let's do complexity analysis now. So the complexity, find the root. That's easy. That's O of 1, because that's just the first element of the array. No problem. Then find the root in the in-order traversal and split it. So finding the root in the in-order like this, here, finding, let's say, 3 here. What is that? Before you listen to me, come up with your own estimate and see if you're right. Pause the video if you need to. So this part is O of n, because the only way we know how to do it, there's no sorting on this list. So the only way we know how to do it is see if the first one is there, see if it's the second one, see if it's the third one, etc., and just walk through the list. That's O of n. So in this case, it's number 1, so it was cheap. But in general, it could be like if this tree had a lot of elements on the left and very few on the right, we might have to walk all the way to the end of the list before we can find the root. So that's O of n. So step 1 is O of 1. Actually, let's put it up here. O of 1. Step 2 is O of n. Step 3, use the lengths of in-orders to find the left. So this could be O of n, because if you wanted to like copy the left subtree and copy the right subtree, but so that could be O of n. But I realize right now that all you really need, like, they're always contiguous ranges like this. It's not like that and that. So you don't really need to copy. All you really need to do is store the indices of the start and end. So that's just some simple math, and actually that's O of 1. And then recurse. So you break down the problem into 2 subproblems. If we broke down the problem into 2 problems of half the size, what would that be? Give it a thought. And if you're not familiar with recursion, I'll have some videos specifically on recursive thinking. But come up with an estimate for if we recurse on an O of n problem at all levels through a tree, what are we going to get? It's tempting to say the answer is n log n, because you split the problem into half at each time, and so there's going to be log n levels of the tree, and each subproblem is going to be half the size of the one above it. But that's actually not true, because we're not guaranteed that the tree is balanced. So the tree could look, and this is a very important case to know about, the tree could look like this, where it's very biased to one side. And actually, if this were reversed, if it were 1, 2, 3, like this, that's the worst for us, because in either of these cases, if the tree looks like one of these, or similar to one of these, this could be a small subtree instead of null, then when we split it into 2 subproblems, the subproblem here is not half the size. Instead, it's just n minus 1. And so we're going to get O of n subproblems instead of O of log n levels of the tree. So really, this is n squared because there is n levels of the tree, and we need to do O of n at each level. So we've now analyzed the complexity of this problem, and n squared seems suboptimal. It might be the best we can do, but it's like if it was O of n, O of n is definitely the best we can do if we can find an O of n solution, because we definitely need to look at each one of these nodes once. There's no way around that. So O of n is the best we could possibly do. And log n, I would have a suspicion that that's optimal, but n squared, I feel like we can probably do better. So let's look through here and see if there's something, some way. Again, we're not coding yet, so we're looking through our plan and seeing if there's a way we can improve it. Well, we can't improve O of 1. So we don't need to look there. So and we can't really improve recursion unless we come up with a whole different strategy. So this is really our only option to improve. Is there a way that we can find the position of the root in the in-order traversal more quickly? Think about it for a moment, pause the video if you need to, and come up with an idea before you continue. So what I came up with is that you can pre-build an index. Like, you can pre-build an index that says 9 is at position 0, 3 is at position 1, 15 is at position 2, 20 is at position 3, and 7 is at position 4, and put this in a hash table. So this is O of n. So we have step 0, pre-build index. That's O of n, but we only have to do that once. So we do O of n, and then we have this index, and in a hash table, looking up in a hash table is O of 1. And so after we have this pre-build O of n overhead, we can change this to O of 1. And so then when we recurse on a bunch of O of 1 things, we have n subproblems, each of which, we have at most n subproblems, each of which takes O of 1, and so that's O of n. And so then if we pre-build the index, then our plan becomes the pre-build case plus the recursive case. So complexity is O of n plus O of n, which is just O of n again. And if this kind of calculation confuses you, I'll have another video, link in the description when I do it, that covers asymptotic analysis. So O of n, like I said, that's as good as we can expect, because we definitely need to look at each node once. How are we supposed to construct a tree without looking at every single node? So O of n is as good as we can do. And so I'm very satisfied with this approach at this moment. And are we ready to code yet? Almost. But I just want to make sure that, and an interview, I'm doing most of this in my head. I'm not writing all this out, but it's important when you're learning to like be very methodical and write out what you know, and you can speed up over time. So how hard is this going to be to write? So I know I'm going to have to pre-build the index, pre-build index. Very easy. I can write that in 1 minute. You just make a hash table and then loop through the array and say, you know, at index 0, or at 9 is at index 0, 3 is at index 1, etc. Super easy. Find the root, super easy. Split the traversal. Well, I just looked that up. Find root, easy. Split at the root. Now that we have this index, you just look it up. Look up root in index. Easy. And then use the lengths of in orders to find left and right preorders. And we're trying to find the index ranges of these things. So there's going to be some index math with off by ones and stuff. So I'm going to say that's like medium difficulty. That doesn't worry me. Uh, if something was hard, I'd want to break it down more or try a different approach. But I'm pretty sure I can do this. And then recursion. Once we have all this information, recursion is easy. So yeah, I'm happy with this plan. So we have a good understanding of the problem, which is step one. Step two, we've generated some ideas, and step three, we've come up with analysis. So now we understand, at this point in the video, you should be able to code this, understanding all the ins and outs. And so that was the point of my video, is to find a plan like this. And then I challenge you to take this plan and convert it into code. This isn't a coding class because I'm assuming that you do have coding experience. And so I'm going to challenge you to do the coding part. So that's it for this time. As a review, step one, understand the problem deeply. Don't code yet. Like, understand the problem as well as you can. Step two, gather and develop your ideas. So try out examples, try and solve the problem yourself and see what mental resources you use, and just gather ideas, see what you observe. Don't start coding yet. Step three, estimate the complexity of both implementing your solution and the algorithmic complexity of running it, and see if you can do better. And decide on a path. You should decide on a path within 10 minutes max, even if it doesn't feel like the best. Like, coding takes a long time. So decide on an approach within 10 minutes, and finally start coding. This is really good for interviews, also because it's not that important if you finish the code within the interview time. What's important is that I, as the interviewer, can tell that you could have finished, that you had a solid plan, that you weren't just floundering and not knowing what to do. So that's another reason that I really think you should hold off programming for about 10 minutes and really explore the space and come up with a good plan. So thanks for watching. I do one-on-one tutoring. You can check out my site on my profile on Code Mentor, and I'm also launching a business, so I'll have those resources up pretty soon. And so I can do mock interviews, and we can really assess your strategies and see where you need growth. And stay tuned for more videos where I do more problems like this, and I go over computer science fundamentals that maybe you haven't seen since college, or maybe you didn't go to college and you just got your experience as a working programmer. I will cover all those things that you need to be an excellent computer scientist and an excellent interview, and nail those FANG interviews. So I'll see you next time. Peace and good luck on your career journey.